All right, Organic Chemistry 2341. Here it's time for homework for chapter 10. Anyway, so let's get a hold of that. Then remember, that's the radical chapter. So we're going to look into the radicals here. Explain the relative distribution of products below from the reaction diagram of the hydrogen abstraction step that leads to each product. Okay, so the rate determining step is that hydrogen abstraction step. So we can look at that and see that there are two different pathways right here. So we have on the first one, we have a tertiary hydrogen. So that is going to be one of the things. And then on this one, we have a primary hydrogen. So remember, there's a difference in stability with those in general. So if we look at just that hydrogen abstraction step, we would say something like this right here would be our primary, right here, hydrogen right here. But for our secondary, it's actually going to be significantly lower to get our tertiary here. Okay, so, and remember, when we have a higher activity barrier, that means it's a slower reaction. Even if there's enough energy in there to get it to happen, which apparently there is, because we're getting 8% of it as the product here, it's still that difference in activity means that this reaction is going to go faster than this reaction, giving us our product yield. Okay. Off to the next one right here. Which of the following compounds can be prepared by halogenation with little complication? That means how is there a difference between materials, etc. So if we look at here, this one right here, this one probably is a yes, because all of these are secondaries, and therefore any one place that gets done will be done in that secondary here. Here we actually have probably a no, because we're going to have 1, 2, 3 different places for secondary, and 2 of them would give the same product. These 2 would give the same product. Plus we have 2 of these right here. So we're going to get a mixture. Okay, we're going to get a mixture of the 2-bromo, the 3-bromo, and the 1-bromo, with the 2 and 3 being about the same because they're both secondaries, and the 1 being a minor component. Okay, so on this one right here, so I'm going to say no for that one. I'm going to say no for this one too, because we have a tertiary site and we have a secondary site. We have 3 secondary sites, 3 primary sites, and 1 tertiary site. So I would expect the tertiary site here to be the most active, and therefore we're going to say no, because that's not going to really do very well. On this one right here, we only have secondary and tertiary. Okay, so we have a tertiary here and a tertiary here, and either reaction at either place will get the same product. So I'm going to say yes with that one. So this one is probably, well, we're going to have a secondary and a tertiary. So we're going to have a mixture of the 1-bromo and the 2-bromo. But if it's only 2 components, then I'm going to say it's not easy, but we can do it. But we'll have to come up with some way to separate the 1-bromo from the 2-bromo. And on this last one, I'm going to say yes, because we only have primaries on here, except that, look at this, it's iodine. Okay, we cannot do radical halogenation with iodine because it doesn't, it's an endothermic reaction. So it's not yes, it is actually going to be a no. Remember, we're only doing chlorine and bromine with these radical reactions. Okay, so let's look at this. Peroxides are often used to initiate the chain reaction and result in this halogenation. Use the bond association energies in table 10.1 to explain why peroxides are especially effective radical initiators, and then write the mechanism of the reaction of the above, showing what could be initiated, how it could be initiated by the diterbutyl peroxide. So let's look at the table right here. I've highlighted a few things that we want to look at. So this is a primary hydrogen for that radical abstraction is 423. This is a secondary, this is a tertiary. So we go from 423 to 413 to 400. So it's dropping 10 and then 13. And then the benzylic here is actually really low at 375. And we know that benzylic site is really good because those are really active. And we have this at 369. So that's about, and that's the allylic. So the benzylic and allylic are even lower than that tertiary, which is why they're more reactive. But let's look at that reaction right here on the peroxide. This is the diterbutyl peroxide. It's 150. It's like a whole bunch less than the tertiary, and even less than half of the allylic or the, so that's why it breaks apart so easily. That's why we like to use it as an initiator. So let's look at that initiation step. We're going to have the first step in our mechanism is going to be having our one electron going this way and one electron going that way to give us oxygen with a radical. And let's put our lone pairs there, just so we know they're there. And then this oxygen is going to give us this radical, and again, with our lone pairs there. So then the next step of this is we're going to have our hydrocarbon right here, and we have a whole bunch of secondary hydrogens. So we're going to react that with our radical. And that's going to do radical extraction. It's going to come over here. Oops, not double arrow, just a single arrow there. And then one of the electrons is going to come this way, and one of them is going to come that way, yielding our next radical. Our hydrogen is still there, but we have a radical on here, and we've made the OH. We've made the T-butanol. So that's what the initiation step is going to look like. And then the next reaction is that that radical can react with, let's do with bromine by itself here. And so that's going to give us our product plus a bromine radical. And that bromine radical can then go and extract a hydrogen, turn it to HBr, and give the process over and over again. Okay, so do you see why we use peroxides? Because that bond dissociation energy is so much less, and we can initiate with them very easily. All right, so let's go on here. We have, starting with the following compounds, indicate each is used in how to do our multi-compound synthesis. So once we make a compound though, like once we make the iodo, we don't have to, we can use it. Now remember, we can't do it directly from this. So on A, we're probably gonna have to do something where we do bromine, and that's gonna get it to our bromide compound. And then we'll have to do a halogen exchange where we have HI in, and then it gives it to there. Remember, we're going to the weaker acid. HI is a stronger acid than HBr, and therefore we can get that exchange. That's A. And then B, we can actually do the same thing. We've already brominated to make this one right here. So what we have to do is we have to make something that has an oxygen on it. So what we'd have to do is take this, do a reaction to where we have an OH on there. So we're going to attack it with a nucleophile hydroxide right here. And that's going to give it. And then we can actually take this compound and do the Williamson ether synthesis. And that's how we can get to this product right here. But it all started with the halogenation step. Okay, so let's look at C right here. In C, we want to form a double bond. So that means we need a one halogen and a hydrogen. So we need dehydrohalogenation or an E2 reaction. So let's go ahead and start with just our cyclohexane plus bromine in with H nu, light or heat. And that's going to give us our brominated material here, Br. And then we're going to hit that with a strong base. It's a secondary, so we can probably use ethoxide and in ethanol right here, O minus. And that's going to give us our alkene right there. Okay, so let's look at D right here. So we want that bromine there. And if we brominated it, we would get a bromine here. So we'll probably have to put a bromine there and then take a bromine away. So let's see how we can do that. We can start with that and do our bromination, Br with H nu, and that's going to give us our bromine right here. And then we can use base ethoxide again right here, and that's going to give us a double bond right here. Okay, and then, let's use HBr with peroxides. It'll give us our anti-Markovnikov product, so we'll get the bromine here. And so that will give us our product. I'm going to put the hydrogen there and the bromine here. So see how we couldn't just directly do it because it was tertiary. So we used that to our advantage to get a really good, a lot of the tertiary material. We turned it into an alkene, and then we used, again, radical chemistry so that we could turn it back over. All right, so let's go to the next one right here, E. And for E, we have to take, we have to do a radical halogenation of, in fact, let me move this product up here so that we can go down. Okay, so remember that's HBr with peroxides. HBr with peroxides. Okay, so let's see, we have our methyl group here, so that means we're going to halogenate it. Let's go ahead and do bromine again. We could do chlorine, we can HNO, and that's going to give us our monohalogenated bromine here. Now we can take our acetylene and put one equivalent of sodium amide right here, and then add it to our halogen here, and that's going to give us one substitution and a hydrogen here. Then we just have to do that again, where we add another equivalent of sodium amide to give us our product there. So this is used a lot. Oh, wow. And the next one, let's see, we got 1, 2, 3, 4. Okay, we got 4 systems. So we're going to probably end up doing the same thing, but we're going to have to do it on the next page because we're running out of room. Oh, okay. Well, let's go ahead and erase that one. We'll try to get it up here. Let's see, so we end up with 4 carbons in our sample on F. So we're going to have to do that same thing where we take our ethyl group. Oh, we don't have to make it because we already made the iodine here. So we have to just take our acetylene with our sodium amide, and then we're going to put in that right there. It's going to give us our starting material here. Okay, now we have our 4 carbons. So now all we have to do is figure out a way to reduce this down. So we'll probably do something like, let's do a reduction and get to our alkene. So just Lindlar's catalyst. Okay, it doesn't matter because it's at the end, but it's still going to give us our alkene right here. And now we want to do a, we probably want to do something like Mercury, Mercurization, Demercurization, and that's going to give us our alcohol on our second piece here. So the mercury acetate, and then reducing it off with the base, sodium borohydride, and that will give us our alcohol on our secondary position right there. So that's good. Now this one's fairly easy because now we already have this. So all we have to do is hit it with a nucleophile. And in this case, we're going to do N3 minus. It's one of the nucleophiles from our chapter 6. So we can use that there. So this is just the one step after you've already made the iodine. Okay, so let's look at the next step here. We have provide the necessary reagents to do the synthetic transformations. So because this is a tertiary alcohol, we can't do an SN2 reaction. However, the first step is probably going to be halogenation to give us bromine. And then we'll probably have to do water. And because we need to make it go in, SN1E1 right here. And so that's going to give us our carbocation, which is nice and stable, and will give us our water here. Okay, let's see what we have with the next one. Okay, so the first thing we're going to have to do is halogenate it here. And then I bet if we did ETOH and base, we would get it to be the double bond. And then we can do our anti-Markovnikov's HBr addition with peroxides to give us our bromine on the number 1 position. Okay, and then we could just take this right here and boil it and react it with hydroxide to make the next product, the OH, or we can take it and react it with the methoxide. Again, it's a primary, so it's going to do the SN2 reaction for both the alcohol, or for the OH and the methoxide here. They're both going to do an SN2 reaction, giving us our products there. So let's look at E now. Okay, so with this, we'll probably have to do 2 steps where we're going to do halogenation to get 1 on there. And then we're going to have to do an E2 elimination to give us our alkene. And then we just add bromine across that in the absence of peroxides, because it can just do that. One's going back, one's going forward. So we have a trans dibromo compound. So we just have to add the bromine to it to get to there. This looks very similar. We're probably going to start with halogenating our material, converting it with an E2 ethoxide and ethanol. And then we're going to hit it with metachloroperbenzoic acid to give us our peroxide. So we had to have our alkene first, and then our peracid gave us our OH. Okay. And let's do, oh, I already did all those two. So that was good. All right, so for each of the following, identify the product that you're going to get A. So what we're going to do is we're going to do it stepwise. We're going to see what each step is going to do. So the first thing we have is Nbs and Orr. How to do that? All right, so what we're going to do here is we have a benzylic position here. So our Nbs is going to brominate in that one. It seems like we only have one equivalent because it wasn't telling us anything else. So we're going to have bromine going there. And then we have palladium catalyzed right here. Palladium on carbon. So that's going to give us our reduction of our alkene, but not our aromatic ring. So we're going to get to there, hydrogen, hydrogen. And our bromine is still here. So then we're adding T-butoxide. So we're going to go ahead and turn it into a double bond. So what we've done is we moved our double bond from this outside position to this inside position, making it more stable. And it's probably going to be the trans alkene. So our A product is this trans alkene. All right, let's go ahead and look at the last one here. We have bromine and light. So we're probably going to do a substitution right here at this site right here. So, and then we have sodium ethoxide right here. So we're going to, our first product is going to be the brominated product, OME. And then we're going to make a double bond in it. I'm going to just put the double bond down there, ME. Then we're going to do boronation dehydration. So we're going to end up with our alcohol over here. So means that our final product, there's going to be an OH down here. So right there. So we're going to have that product as our final product. And that is the end of chapter 10 homework. So I'll post this and you can have fun with it.